Ideal gas law. And this is how we get it from all of those other gas laws we've done. A side note, we always must use the temperature in Kelvin now because the units are tied up in the gas constant. And if you don't use Kelvin, you won't cancel your units correctly. Let me give you an example. First of all, just to use Charles' law, volume is proportional to temperature. What do I mean by constant? Well, constant is where we make the relationship direct by using a fudge factor or a constant. So V isn't just proportional to T, V equals T when I put in my mathematical constant K. That constant is sort of like how pi works in circles. Doesn't matter what the size of the circle is, pi is always the number in there that makes it work. That's what our constant is. Now, because the constant has been created by much smarter brains than me, they've used the unit Kelvin. So whenever you use temperature here, in order for it to cancel with the unit in the constant, you will need to use Kelvin too. Long story short, always use your volume in liters, always use your temperature in Kelvin. And we have Boyle's law, just a very quick recap, that pressure and volume are opposite. As pressure goes up, volume goes down, and this is called an inverse relationship. Gay-Lussac's law, pressure is proportional to temperature at constant volume and number of moles. Avogadro's law, that volume is proportional to the number of moles at constant temperature, pressure, and volume. Now, this is actually the one that you would have used if you did magnesium plus hydrochloric acid in your depth study. The side note is that for any gas, hydrogen, oxygen, helium, 1 mole will always occupy a set volume. And that's really interesting. Doesn't matter the size of the gas. It's always the set volume. Now, this is where I got it wrong for your depth study this year. I'm sorry about that. I was talking about standard temperature and pressure, but I should have been saying standard lab conditions. So room temperature, which is 25 degrees or 298 Kelvin, and normal atmospheric pressure, which is 100 kilopascals. Any gas will have the volume of 24.79 liters. That's really interesting. Last but not least, I'll recap that again. Standard temperature and pressure is freezing point, 0 degrees Celsius. I should have said to you guys before in your lab that it was standard lab conditions, which is room temperature 25 degrees or 298 Kelvin and then 100 kilopascals. Either way, this still remains true. For any gas, 1 mole will always occupy a set volume. And in room temperature, the volume is 24.79. So to lay out my laws so far, here I have them, and I'm just going to swap the P with the V there so that I can do some rearranging. If I have all of these laws and I color code, I collect all of my like terms. I collect all the V's. Come to me, V's. I collect all of my proportional signs. And then I just really collect the rest of my terms and arithmetically just put them into a little equation like that. Then I'm going to collect my P, bring it back up to the top, and that means my pressure and volume is proportional to the number of moles and the temperature, times 1. Now this is where I get rid of my proportional sign by bringing in the gas constant. Now just like pi, the gas constant is a number that doesn't change and allows me to say a direct relationship. This is the ideal gas law. PV equals nRT. It's not a huge part of our course, but it is a huge part of chemistry. The ideal gas law is what you're going to be using to calculate pressure if they give you the volume and the temperature. Or it'll be what you use to calculate number of moles if they give you pressure and volume. Again, it's just a little bit of algebra, but you'll be rearranging this equation in order to solve for any of the terms. My hints to you, P always convert to kilopascals, volume always convert to liters, N stays in number of moles, and T always have in Kelvin. And the reason you need to do all those set units is because R has a very specific set of units too, and they won't cancel unless you convert them into the right liters, the right units. That makes more sense. Now, PV equals nRT is the ideal gas law. And what that means is I guess it's an imagination of a gas. If we imagine gas particles to be floating freely, and when they bounce into each other, they bounce off elastically and they don't lose any energy. That is what an ideal gas is. It's not reality, but it's a really nice approximation, and it leads us into this idea, and it makes us, really convenient, because then we can use this equation right here. Ideal gas law.